Okay, so we have seen the formula for potential due to various charge distribution. And we know the potential is defined in terms of work done per charge in bringing something from infinity. But you will come across a variety of situations in which the distribution of charge itself is spread up to infinity. So if the distribution of charge itself is spread up to infinity, in such case, we cannot define potential. So if I say this is the infinite line charge, so if we have an infinite line charge, and if I ask you, can you define the potential at a point P? So the answer is no, we cannot define. So why we cannot define? Because here the y itself is infinitely long. So can we go away from the y?
Sir, what about on the other axis?
No matter which axis you see. Let's say I'm saying there is a building of infinite length. So if something is technically infinite, so it will be visual from any place in the world, universe.
Yes, sir.
So the whole idea is, if something is infinitely large, then we cannot define the potential, because the infinity, you cannot go away from the distribution and you can call it in. So if let's say if I'm saying this is infinity, so infinity means, first of all, this should not have any influence. But if you go to infinity, the charge is also as big as possible technically. So it will be like a visible to you. So you cannot say, okay, there is no potential here. The idea is something which is infinitely long or infinitely spread, the infinity is not defined. That's the whole idea. The second thing is, infinity should be defined not at one place, it should be defined in all directions equally. For example, you're saying that we can have infinity here, but we cannot have infinity here, right?
Yes, sir.
So there should not be any kind of ambiguity or like a constraint about choosing the infinity. So that if there is a constraint in choosing the infinity, it means we cannot define. Okay.
Yes, sir.
So because it is going up to infinity, so some charge will also reach the infinity. So now the potential at infinity will be non-zero, and therefore the work concept will fail here. So let's say if you still want to define the potential difference, the potential difference at infinity will have some finite value, and the potential at the point P will have some value VR, and then you can still define the potential difference. So that we can define in terms of work done per charge. So we can say that if I bring some charge from here to here, then work done we can write as Q into VR minus V infinity. And the work is like we know the formula for the work, but it's a line charge. So things will be difficult. So you can see the work done per charge is not VR, whether it is VR minus V infinity, and therefore the potential at R will be the infinite potential at infinity, which we don't know. Because this term is unknown to us, we say that we cannot define the potential for such a distribution. But in such case, what we can define is called potential difference.
Yes, sir.
And so we cannot define potential, but can define potential difference. And why we can define potential difference? Because if you remember the definition of potential difference, delta V, it is minus E dot dr. So if electric field is existing in the space, then the difference will be there, isn't it?
Yes, sir.
So this formula says that okay, you can always calculate the difference. So let's say if I look at the top view of this wire, so let me create a top view of the line charge. And this view we represent generally by a circle. And if the charge is positive, you can just write a positive sign. Or if it is negative, you can just write the negative sign. So this will be lambda. So when I represent something like this with lambda, what you should understand is this is the line charge, not a point charge, right?
Yes, sir.
And also you have to understand this is like infinitely long. So this is really big. So this is like, okay, without default, it will be infinity. I mean, generally it will be mentioned in question, but here I'm not saying anything. You can understand it's infinite. So let's say if I try to draw the electric field lines, we know the field lines will be concentric circle, right? No, the field lines will be radially outward. So if I draw the concentric circle, so here the electric field lines will be like this in the radial direction. If you look at the view in the plane, right? So any infinitely long line charge creates the radial field, isn't it?
Yes, sir.
Do you know this? Yes or no?
Yes, sir.
Just so although we do not know the potential at any point, so let's say the inner radius is A and outer is B, but the potential of this point and potential of this point, we can find the difference. Why? Or how we can find the difference?
So because we can find, we can find out like the difference between the positions of the 2 points.
Because the potential, the unknown term, when you take a subtraction, the unknown will vanish.
Yes, sir.
So although the unknown is there, but while calculating the difference, the unknown will be equal for both, and therefore it will cancel out. So that's why the difference is possible to calculate. Okay.
Okay, sir.
So how to define the difference is simple. So we can write as, because the electric field is like this. So which one is at high potential, P or Q?
Sir, P is at high potential, sir.
So we can write the high minus low equals to E dot dr. See, when I write the value, I have to be careful about the direction. But if when I write the delta V means final minus initial, then minus will come. Okay.
Okay, sir.
So the value of E is how much? If you remember, and the dr is parallel. So this is E dr. So I'll just write a VPQ in short to save the space. So the electric field formula for the line charge is what?
Yes, sir. K lambda by R.
K lambda by 2K lambda by R.
Yes, sir.
So this turns out to be how much answer? The answer turns out to be lambda upon 2 pi epsilon not ln B by A. Is this clear?
Yes, sir.
All right. This is a very famous example, and the difference we can write, and because we can write the difference, we can write the other thing as well, like work and all. Okay, so now we can take an infinite sheet. So let's say we have an infinite sheet, but with a uniform charge density. And what I'll draw is just the side view, not the front view. And the charge is here. So we know due to the infinite, if it is infinitely large sheet, the electric field will be how much? Sigma by 2 epsilon naught, right?
Yes, sir.
Now again here can we define the potential?
We cannot define the potential, sir, but we can define the potential difference.
Right. So let's say if you go from A to B via some random path such that the displacement along the A along the field is, let's say this length is A, this length is B. So which one is at high potential, A or B?
Sir, isn't the field uniform?
Yeah, of course field is uniform.
So since the field is uniform, there won't be any change in the electric field, so it will be constant, right, sir?
Yeah, the field is constant, but the potential will not be constant. No? So what is the potential formula? Like E is minus dV by dx. This. So even E is constant, dV will be there, no?
Oh, we just while integrating, we just take the E outside.
Yeah, that's the only difference. So no need to integrate here. This is very simple question because E is constant. So if a constant field, we can just write the potential difference as E into displacement in the direction of E. This is A only.
Yes, sir.
The potential difference has nothing to do with the path taken. Understood?
Okay, sir.
So because see, if the field is right, so it means the potential will change along the right only, na?
Yes, sir.
So the potential only changes along the field direction, not in the perpendicular direction. Okay. So the value of magnetic field will be EA. The path will not matter, B will not matter. What will matter is just A will matter. Okay.
Okay, sir. Since the potential will be constant for like when we take a layer that's parallel to the plate.
Yeah. Because if you work like this, the E dot dl will give you 0 answer.
Yes, sir.
Also, you can think this way. See, if you work perpendicular to the field, the work done is how much? 0 only, no?
Yes, sir.
So everything depends on the flow. So potential only creates the difference of potential creates the electric field difference. So even the electric field is constant, the potential must be changing. Then that's why we have the field, and the electric field always go from the high potential towards the low potential. That's the simple logic. So
Okay, sir.
field is constant is not doesn't mean that the potential will be constant. When field is 0, then potential is constant. Understood?
Yes, sir.
So the A will be at high potential, B at low. We can write as E into A, which is sigma upon 2 epsilon naught into A. And that's the answer. It's clear.
Yes, sir.
So sometimes just to confuse the student, the questions are made like this, some random. So let's say we have a field along the x-axis and a charged particle. So electric field is along the x-axis. I am having the formula E not xi. So field is along the x-axis. Okay. And the
Yes,
charge, a charged particle is like a bouncing ball. So let's say you take a ball and you throw it. So it bounces like this. Okay, it is bouncing like this. Assume it. So if you want, you can convert into some function also. And let's say the equation this path, this is path. And the path equation is y equals to 2L by pi something like this. It's a square function. And what else I can understand here? So 0 means okay. So the y will be 0 when the sine angle is n phi, correct?
yes, sir.
So if I let me remove this part. So if it is a sine function, when y will be 0? When sine square pi x by L is 0,
Yes, sir.
and sine of theta is 0 when theta is n phi, right?
Yes, sir.
So x, the value of x at which the answer will be 0 is x equals to 0, L, 2L, 3L, and so on.
Yes, sir.
So this must be 0, so this must be L, 2L, okay?
Yes, sir.
So if I call this as O, this is called this as A. So what is the potential difference between O and A?
Sir, 2 E naught L square?
Yeah. So the answer will be again because this is E naught x dx, and you're going from 0 to 2L, right?
Yes, sir.
So the answer is this is 2 E naught L square. This is what you said, right?
Yes, sir.
So what you need to remember is once you know the direction of electric field, just you have to bother about the direction of field, and you have to find the displacement in that direction and also do the integration in that direction. Okay,
Yes, sir.
rest is not required. Okay. So now imagine we have a situation like this. So we have a like a XY plane, and the origin is a place at which we have a fixed charge Q. And there is a line on which a charge particle is moving. So the line is cutting the x-axis at a comma 0, and it passes to the location called 0 comma b, and this charge is moving this way. That's called Q. Okay. So question is find the maximum potential energy between these two charges. So find the maximum possible potential energy of system of charges uh, okay,
Yes, sir.
and assuming it's coming from infinity, so you can assume that this charge is coming from infinity. The second question is find the minimum kinetic energy given to charge Q such that it it continues its journey along this line in the same direction. Okay, so now these are two questions. Think about it, what I'm saying, and then I'll solve. So are you finding it difficult?
Sir, I'm getting the answers.
So what is the answer for the first part?
So for the first part, I'm getting the answer as KQQ under root A square plus B square by AB, sir.
Yeah, very good. Like this one, right?
Yes, sir.
Very good. So the maximum will be where at the nearest point, right?
Yes, sir.
The
And
nearest point is
for,
perpendicular, right?
yes, sir.
And the clue is here only. So now you can understand the why this.
So twice of that value is the minimum K that should be given to the charge.
No, not twice. Just exactly same answer. See, when the charge is at infinity, there is no energy. Okay. So initial energy is how much? U initial is 0.
Yes, sir.
Since Q is at infinity. All right. So
Yes, sir.
what will happen is if you don't give some, let's say, kinetic energy, then this charge will repel, isn't it?
Yes, sir.
So if I think like, okay, this is like a some sort of a bamboo and or a pole, and there is a charge wrapped in a ring. Okay, so this is a charge ring, and this ring is thrown. So what will happen? This capital Q will repel. So repulsion will only occur till this point, no?
Yes, sir.
Because anywhere before will have the repulsion component, which will try
Yes, sir.
to decelerate you, isn't it?
Yes, sir.
The moment you cross this point P, the same charge will support your motion
Uh,
because the
Sir,
repulsion.
so we are assuming that deviation will not be possible by the moving
Yes.
charge, sir.
Yeah, deviation is not
So,
possible. It's like you're, I mean, because of some reason you continue to move like this only, always.
okay, sir. Sir, I thought like because we are taking into account the deviation, we have to still do some work to again keep the
Okay.
charge in track.
To keep the charge intact, we can create a groove kind of thing, or maybe like the situation which I have created, and that will not require any work. So the idea was like we have to provide energy to overcome the repulsion, isn't it?
Yes, sir.
So if I cross the point P, my job is done. After that, the charge plus Q itself will support my journey.
Oh, okay, sir.
Do you realize this? What I'm saying?
Yes,
After
sir.
point Q, after point P, the capital Q will repel you, and that will help you in a way to continue moving in the direction. So imagine if the velocity is not given to the small charge, it stops here, then the repulsion
Yes.
will send you back.
Yes, sir.
So by any chance, if you stop before the point P, you will go back, and that is not something which we don't want. So the equation we have to write is the U final will be U max, and then you can add the K initial as half mv square, and the K final we can take as roughly 0 because I'm just about to cross the point P. So I'm slowing down, but I should have the sufficient energy to just cross the threshold, right? So
Yes, sir.
from conservation of mechanical energy, we can add half mv square equals to kqqq under root of a square plus b square upon ab. Okay,
Okay, sir.
and then rest if you want you can solve further, but this is the whole idea. If you have doubt in this, please do ask.
Sir,
There is
no, sir. First, I didn't understand the situation correctly.
which relation?
Sir?
Like you have some doubt?
Sir, no, sir. No, sir. At first, I told like at first I didn't understand the situation
Okay.
correctly.
Yeah.
I thought that we were making the charge move at the same time.
Yeah. All right. So anyway, this is the D, and the D is this is something which we have seen before also in kinematics or somewhere in angular momentum also, right?
Yes, sir.
So the same question we can recreate in a slightly simpler fashion, and let's say just let me make it simple. So we have a isosceles triangle. Simple question. A 0 0 A plus Q fixed, and a charge which is bound to move along this groove. Let's say if you, because it will help you of charge Q and mass M. So what is the minimum velocity we need to impart from this location so that it should reach the other end? Like it should just reach the other end. That's it. It can go beyond that also, but our idea is it should go on the at least it should reach this point. That's it. So find minimum speed imparted to the charged ring such that it can reach the other end. Maybe you can say B point, and let's say you release from A point. So what we should do? Tell me what we should write here.
So we should frame the situation such that the um, velocity becomes just zero when we like at the point where there'll be the maximum repulsion. And
Yeah.
after that, when we draw the vector sign, we can see that the force will be supporting the motion of Q.
So again, it's the same question. You have to cross the point P.
Yes.
So the potential will be maximum at point P, right?
Yes, sir.
So the work done or the energy imparted should be equals to Q into Vp minus Va.
Yes, sir.
You can add the way you want. I mean, this I'm writing in one line. So the half mv square is equals to Q, and Vp we know the formula. What is Vp?
Vp will be KQQ by root 2
D.
KQQ by A. Yes, sir.
So the D in this case is simple. No? So it is A square by root 2A, right?
Yes, sir.
So it is A by root 2, isn't it?
Yes, sir.
But A will also have some potential. So earlier the charge was coming from infinity, so the potential was zero. But now it's coming from the nearby location, so it will have the potential.
KQQ by A.
Sorry, we should not add this value. We are writing potential, no? Not the energy. So
Yes, sir.
potential due to the other charge, right? So this will be KQ by A. So the answer will be half. So this is a really nice answer. Correct? Like this.
Yes, sir.
And then you can solve. So they may ask you just find the potential energy, kinetic energy, then this is the answer. They may ask you find the speed, you can do it further. Okay. So the third case will be what if I consider the gravity also, and if I make this as a vertical plane, and things will change in that case. Okay. So the third, you can say variation of such problem is making the diagram in a vertical plane and considering the gravity. So the next example is assume the previous case as motion in vertical plane under uniform gravity. If I intentionally give you G, I expect that you will be using the G also in a formula, right?
Yes, sir.
So a small change will occur in writing the equation. Rest is going to be same, and I hope you can figure it out easily. What is the possible change, right?
Yes, sir.
So now, what is the minimum speed required to reach the other end? This will be like, I think, very complex answer. It's going to be complex.
Yes, sir.
Hmm. Think about it. I mean, yeah, this is going to be a tough question. I just made this question. This is a question which I never gave to any student in my life. It's a fresh from the oven.
Okay, sir.
Then we can discuss. It's a really nice problem. I think it may be mathematically challenging. I don't know. I mean, how difficult it's going to be, but hopefully something we can do.
Okay.
See, even I'm not sure whether this is doable or not, but I'm just thinking about it. So don't worry if nothing goes. I mean, if something is not coming proper, that's okay. This is like experiment.
Okay, sir. So,
So I think it's mathematically cumbersome.
sir, I'm not sure like if I have interpreted it correct or not, but then we are just adding another component of uh,
Gravitational potential,
mg.
right?
Yes, sir.
Yeah. So if you choose a random point P, so now we cannot say that this will have the maximum potential, right?
Yes, sir.
Because even gravity is kind of opposing, na? So now
Yes,
I
sir.
will take a general equation and I will call it let's say a variable L. Let's say L is a variable.
So what if we consider the x-axis to be the ground?
Yeah, you can take no ground.
So
So now if L is variable, then tell me what is the potential, gravitational potential? Mg L by root 2.
yes, sir.
Okay. Now the next part is slightly challenging because now we have to find the new separation, maybe something Z or maybe a D. So now I have to calculate D in terms of L, na? And A is D. This is A, and this is 45 degrees. So we have to use the cosine formula. So cos 45 degree equals to A square plus L square minus D square by 2AL, correct?
Yes, sir.
So the D square turns out to be how much? A square plus L square minus 2AL cos 45.
Yes, sir.
So D square is actually A square plus L square minus root 2AL. L is variable. Keep in mind. L is, so D turns out to be how much? Like this. And now the electrostatic potential, or what we call is the mutual potential, this we can write as how much? So we are
D.
going to we are going to ignore the gravitational potential energy of the two charge particles. We'll just take the Earth and the charge because the mass of the particle is very small. So the mutual will be K Q by D, right? And the total will be how much then? If we have the two formula.
Your voice is cracking.
Am I audible now?
Yes, sir.
So what I'm saying is that we got the gravitational potential as a function of L. We got the mutual potential as a function of a D, which is itself a function of L. So the total potential will be how much? Mg L by 2 root 2 plus KQQ by under root of this big term.
Yes, sir.
Okay. So maybe the idea which I am thinking is we have to maximize this function, isn't it? We need to know where it is maximum, because if I can achieve this energy, then it's easy for us. So the question is where it is going to be maximum. The sum should be maximum, not the individual value. Earlier we had only one formula, so it was easy, right?
Yes, sir.
But now it is not easy. No, it is not easy. No. So for U total max, you can clearly see it's a function of L. So du by dl must be 0.
Yes, sir.
And if I differentiate, I'll get mg by root 2. And this term is root function. So it will be how much? If you differentiate, 1 by root x is how much? Minus half power minus 3 by 2. So you
Yes, sir.
can take common k and x per, okay, we'll just do it differentiation. So root x, sorry. So d by dx of x power minus half, and this will be minus half x minus 3 by 2, which is minus 1 by 2 x root x. That's a formula. So this will be similar to this answer, minus 1 by 2. Oh my God, who will add all this thing? So what I'll do is let me differentiate this separately. Uh, so I'll differentiate this term separately and then I'll substitute. Else it will be very complex. So this is some box. So if we have 1 by under root of a square plus l square minus root 2 al, and we are trying to differentiate with l this entire term, the answer will be, so you can use the division rule also. So differentiation of u, which will be 0, will be minus 1 into differentiation of this will be 1 by 2 root. And then we differentiate inside, which is 12 minus root 2 upon v square. So this entire term turns out to be minus 2. Okay. So having this answer, now we can substitute, right? Very bad answer. So we have mg by root 2 minus k cube q into 12 minus root 2a whole upon this, and this we have to equal to 0, right? And this is
Yes.
like we cannot solve. That's because this is mathematically impossible to solve the some random power equation, because we have L here, L here, L here, so we can't solve. But okay, this is the condition for. Okay, I will not say anything. This is the, I was expecting something like this only, and yeah, I got something like this only. So let's ignore this question. Yeah, right.
Okay, sir.
But this is good learning. So this is something okay. I mean, maybe we can create in future something like that. So we'll do some easy problem. Like we have been doing really tough problems. Let's do something.
Can I just move my laptop to somewhere else? Your voice keeps breaking.
No, I can't move anywhere because the place where I'm sitting is the.
I move my laptop?
Yeah, yeah, you can move. Yeah.
Sir, are you able to hear me?
Yeah. Okay. So am I audible to you now?
Yes, sir.
Okay. So this question is called the distance of closest approach. So let's say we have a big charge, maybe like a nucleus, you can think of like a Rutherford experiment. And this is a fixed charge, which means it cannot move anywhere. And from this charge, from very far away, which we call infinity, which may be even 1 centimeter. So infinity is just a relative term which you know. So now you project a small charge with some velocity v naught. So as the charge will move, repulsion will slow down, correct?
Yes, sir.
So at some point it will stop, right?
Yes, sir.
So we say that this is called the distance of closest approach, d. So if v naught is given, q is given, small q, capital Q, mass is given. Can you find the capital D?
Yes, sir.
Find the distance closest approach, which we represent by symbol d. So it's pretty much simple question of energy consumption. You get all answers, right?
So mass.
M. Take it.
So 2
Yeah.
kq by mv square.
Yeah. So the answer you're writing is half m v naught square equals to k q q by d, right?
Yes, sir.
Excellent. So this is the answer. So it's a very simple answer. 2kq.
Call from India +911449.
Okay.
Yes, sir.
So
Yes, sir.
the second scenario is, what if the, so of course I am throwing from infinity very far. But the other charge, which earlier was fixed, is also having mass m, charge q, and it's free to move. So as the small charge will approach, the big charge will also try to accelerate towards right, isn't it?
Yes, sir.
So then how to find the minimum separation? What is the distance of closest approach now? To find d minimum again, what will be the minimum separation between them? So what you will do here? Think about it. So what we need to conserve? So this is like a same question like a spring problem, no? If you remember the spring problem. So this is again a simple question. I think you are
Sir,
getting now.
no, yes, sir. I'm doing the calculation part. Just a second.
So just tell me what are you conserving here?
Sir, I mean, like the system as a whole, sir. In there, like at the final, both the velocities will be equal.
Right, very good. So it is the conservation of momentum, right?
Yes, sir.
Yeah. Very good. So I think we'll get the answer. Yeah, go ahead.
So,
Yeah,
so mm by m plus m is the reduced mass, right? So,
yeah, right. Exactly.
so then I'm getting kqqq by half mu v naught square. So,
K cube Q by half mu peanut square is the right answer. So in fact, you should have written the same thing. In the CM frame, when both will move together, in the CM frame, they will be at rest.
oh, yes, sir.
So if you remember the formula for the kinetic energy in the CM frame, which we write by K mu, will be half mu into U relative whole square, which is V naught square.
Yes, sir.
And this energy at minimum separation becomes potential energy. So this is the energy which will eventually become the potential.
Yes, sir.
So this is just one form of energy will convert into other form, and that will give you the answer directly, right?
Yes, sir.
So center mass concept you can apply here also. It's not that difficult. Okay.
Okay, sir.
So you can also play with this concept with any shape, need not to be just particle. So maybe I can give you, let's say there's a gravity free space, and you can think of a disk. So you can just create this hypothetical disk in a gravity free space, and the disk will have the radius some value called r, and sigma is the surface charge density, and mass of the disk is capital. And again, along the center of the disk, I throw a charge of value charge, and disk and the so the only force between them is electrostatic force. So again, they will separate, right? So if as the cube will approach, the disk will try to move away because of repulsion. And if I ask you the same question, what will be the minimum separation? Same question. I'm still doing the same question. Minimum separation problem. So what we can write? So it's a same answer. Just the formula for potential energy will change, isn't it?
Yes, sir.
So can you try this question?
Okay.
I think yeah, it's going to be complex only. But anyway, you can try.
Okay. Okay, sir.
At least write the equation, then I'll just check.
Yes, sir. So
Yes, tell me.
half mu V naught square is equal to Q sigma by 2 epsilon naught into under root T square plus R square minus T.
Yeah, so now we have to add Q into potential of the disk, right?
Yes, sir.
Which is under root of d square plus r square minus d, right?
Yes, sir.
So this seems to be difficult only.
There's a quadratic involved, I think.
Yeah. So if I, okay, this can be solved if I make, so okay, this is the equation which is correct. So let's say, let the distance of closed approach is much bigger than r. Then we can solve, no?
So then 2D and we just bring everything to the other side.
Then this will become how much?
Into
We can
2D.
yeah, we can write
Sorry.
1 plus r square by d1 1 by 2, the binomial approximation,
Yes.
minus d, and the d will now cancel out. So what we get is, yeah, something like this, r square by 2d.
Yes.
So no, d we can find at least, yeah, sigma. Okay. These kind of approximations are very common in physics, and one should be very much well versed with this approximation technique, like what we should do to get the answer. So this is called the first order approximation. Sometime in question, maybe in the last lecture, you have seen the second order approximation. So we have gone to the
Yes, sir.
x square term, right?
Yes, sir.
So 99% question of J advance only deal with the first order approximation. Maybe 1% in Olympiad, they go for the second order approximation. So in fact, they give hint also in the question itself. When I give question, I don't give hint because even I don't know what I need in future. Okay. So after distance of closed approach, we can solve some very generalized question which are based on energy conservation. So maybe I can create a question like this. So imagine we have a disk and you remove a part of it. Okay. Anyway, so now the disk is uniformly charged. And this height we can call is h, and gravity is there, g, or we can ignore the gravity. It will make it things unnecessarily difficult. So let's say there is no gravity. Now we have a minus, means some negative charge particle of charge minus q and mass m, and it is released from rest. So the disk will attract, isn't it?
Yes, sir.
Sigma is the surface density. So when the charge is crossing the center of the disk, what will be its speed? So find the speed of charged particle at the instant it crosses the center of disk. Okay.
Okay, sir.
So now what you're doing is the same work energy power chapter we are revisiting in a electrostatic scenario.
Yes, sir.
So if you remember, I told you that in class 11th only that 12th is just application of 11th with some new formula.
Yes, sir.
And if you look carefully, that every formula we derive using the work definition, isn't it?
Yes, sir.
So essentially, learning 11th is sufficient, but 12th is somewhat complex in terms of theory only. So you have
So
come across many theory now.
we familiarize ourselves with the theory.
Yeah. So once you get familiarized, then you won't find the difference between the two portion of 11th and 12th. And I hope
Yes,
that
sir.
you are finding 12th easier than 11th, isn't it?
Yes, sir. It's just like the information that's so much.
Yeah. So much information. That's the only difficulty. But it is like with time you can digest eventually. So it takes some time to kind of make a memory muscle towards all this information. So in the beginning it's difficult, but if you go for twice or three revision, that is sufficient. Okay.
Okay, sir.
Next, I'm going to share a book with you. So since you're revising 11th, then I'll suggest that don't just revise the numerical, but you should have a really nice revision of theory also. So the book which I will share is really good. You can refer for some good chapters like rotational, momentum. So that will strengthen your knowledge about theory, and that will help you tremendously in J Advance. So I'll share that book also.
Okay,
But
sir. Which book,
yeah,
sir?
it's a some foreign author. It's called the book by the Paul A. Tipler.
Sir?
Okay. It's some. I mean, I'll just share. Just a minute. Tipler. There is called there is an author called Paul A. Tipler. I'll come to that.
Okay, sir.
Okay. Yeah. So going into future, some theoretical strengthening is also required if you want to really get a very good rank in J Advanced. So to get into the top 100 or 200, these readings are very much important. Okay.
Yes, sir. Since many of the trick questions will come from theory only.
Yeah. So the familiarity with the theoretical knowledge is equally important. That makes things really easy actually.
Yes,
So
sir.
numerical we are anyway practicing in class. So we are solving a lot of numerical. If you realize that what we discuss is numerical only.
Yes, sir.
Yeah. Okay. Anyway, solve this question quickly. Just start the equation. I just want to see the equation, not nothing much.
Okay, sir.
Okay. Try this out.
So can I just come back in a minute?
Yes, yes.
So,
Yeah.
sir, I'm getting the answer is Q sigma by 2 epsilon naught into under root h square plus b square minus under root h square plus a square is equal to half mv square plus q sigma by 2 epsilon naught b minus a.
Okay. Let me just check. Big thing. So I think the initial potential is how much? Minus
So,
Q potential due to the disk, right?
yes, sir.
And the answer is simple, which you have done already. So sigma by under root of h square plus b square minus a square. Right? This is the answer.
Yes, sir.
And the final will be how much? The H will be 0.
Yes, sir. So B minus A.
So it's simply B minus A. And then we write the energy condition. So Ui plus Pi is Ua plus K. That's it, right?
Yes, sir.
So that's what if you have done this one, then this is correct. Very good. So they will generally give you the values which are nice to solve. I mean, of course. So now you can understand why the formula U equals to QV is so important.
Yes, sir.
So next part is now this is technically very important concept, and this we call aiming parameter. So this is basically pertaining to the Rutherford alpha scattering experiment. So let's say we have a nucleus with charge, and of course nucleus is like a fixed value, so you can think as fixed place. So whenever we have a charge system with some of the charges are fixed. So to fix, when I say it is fixed, it means some other force is holding it, right?
Yes, sir.
So by default, external force is present in the system.
Yes, sir.
So you cannot conserve the momentum. You must have realized that momentum is only conserved when both charges are free. There is no one who is holding it back.
Yes, sir.
So now this is the fixed charge, and let's call the charge as Q. So there are two types of questions we come across. So generally, uh, from a given height, which we call the aiming parameters, we call it B, we project another charge point. So generally we project as fast as possible. And if you project it, so initially it's at infinite separation, so nothing will happen. But as it will start coming closer, the repulsion will start pushing this charge like this. Understood?
Yes, sir.
So this will be the path traversed by the particle. All right.
Yes, sir.
If the repulsion is really high, then it may bend like this also.
Yes, sir.
Okay. So variety of paths is possible. I'm just taking some path, random path. And now you can see the minimum separation between the charge and the path is this one. So this is the D minimum. You can call it any value. You can call it D. So question is, if this charge is Q and mass is M, find D minimum. That's the question. So again, this is called distance of closest approach when the line of motion is not the same as line joining the charges. Earlier, the line of motion was same as line joining the charges, right?
Yes, sir.
So what will happen if we have situation like this? So what concept we have to apply to deal with this problem? Or simply speaking, what are the conservation law we have to think about? Yeah, velocity given is V naught, so my bad, my bad. So we give V naught. So you can think for like 10 minutes, then I'll solve. Okay. So you got the idea? Some idea? Okay. No. So first of all, the force is acting between the two charges, right?
Yes, sir.
So whenever we have a fixed charge, the torque about the fixed charge will be zero because the force will pass through that line, isn't it?
Yes, sir.
And if the torque about a point is zero, always we know what is conserved.
The angular
Angular
momentum.
point. Correct. So now here the first step of solving is assume some speed here and write from conservation of angular momentum with respect to or about fixed charge. What we can write? So what is the momentum? So for a particle, the only momentum is called the orbital, right? We don't have the spin.
Yes, sir.
And orbital only depends on the perpendicular separation. So for the initial velocity, what is the separation between the charge and the V naught?
Sir, the initial it's B.
Yeah. So the how to write the angular momentum? What we should write here? What is the formula for the orbital? I think we don't remember. Huh? It is RC cross VC. Okay, for body, but for particle it's just M R cross V. Okay.
Yes, sir.
Okay. So now the answer is simple. How we write is M V not B. So for this line of motion is how much? The B distance away.
Yes, sir.
So the angular momentum we write is M V. So the we only take MVR. The R is the perpendicular separation on the line of motion and the given charge. Okay.
Okay, sir.
And then now you can see the velocity vector is again like this. So it is MV, which we don't know, D minimum.
Yes, sir.
So the D minimum, oh sorry, not D minimum, I can say the V, which is also unknown, is equals to V naught B upon D mu. And we need this equation later on. The second equation will be conservation of mechanical energy. So the initially the only energy is kinetic energy because it's very far, so there is no potential.
Yes, sir.
But when you come to the nearest point, you have kinetic energy and a potential, which we write as K Q by D minimum. Okay. And now you can see that intentionally the V was unknown. Now we have the relation. So can we substitute?
Yes, sir.
So this is very famous equation which you will come across to solve. I'll tell you how to solve this equation. So the way of writing is half m v naught square is half m v square plus k q. I'm not writing d minimum because I'll write at the end the d minimum, just d. Okay. And
Okay,
now
sir.
I can write v as v naught upon d. Correct.
Yes, sir.
So if I multiply both sides by 2, or yeah, so half m v naught square equals to half m b square v naught square by d square. Now you may think that this is difficult to solve, but this is very easy to solve because it's a pure quadratic equation. So let 1 by d as x. This will be easy now. So this will become half m v naught square equals to into x square plus kq qx, right?
Yes, sir.
So now this is a quadratic in x which we can at least solve, right?
Yes, sir.
So I can write as let's multiply by 2. This is the answer. And okay, of course, you can simplify further if you want. But this is the answer of 1 by d. I can just invert it. So the d minimum turns out to be how much? Generally, while writing, we take the common and we make it simple. But I'm just writing the raw form. So really bad answer, but that's okay. A similar question comes in gravitation, in which attraction will pull the object towards it. Okay. So the conservation of angular momentum questions are very common. Whenever we have motion around some fixed mass or fixed charge, automatically the torque will be zero, and you can always think of the conservation of angular momentum part. Okay, especially the orbital angular momentum. Spin will not come here because we deal with the particle.
Yes,
Okay,
sir.
all right. So now we can go next. So what is the other variety we can do? So let's say we have a problem like this. So these two are the two coaxial rings. So these two are the two coaxial rings. Okay. Which means they have the same axis. And the separation between them is d, and the charge is given is q1 q2, radius is r1 r2, and these are fixed. No need to worry. So there is a charge q naught which I would like to take it from here to here. How much work I need to perform to take this charge from there to there? Simple, but nice question. Think about it. It's easy.
I don't understand why D is given.
Pardon?
Sir, I don't understand why D is given.
So tell me, what is the potential at the beginning? Let's ignore the Q naught. What is, let's call it A and B.
All right, we
The
are taking the net
potential.
potential at both due to both the
Yeah.
charges.
Yes, of course.
Yes.
So the D will come, no?
Yes, sir.
Yeah.
So,
Yes.
I'm getting the answer as Q into KQ1 by under root x square plus R, I mean D square plus
Yeah.
R1 square plus KQ2 by R2 square, sorry, not just R2
Yeah. Yeah.
minus KQ1 by R1 minus KQ2 by
Okay. So
under root
yeah,
x
the
square plus
better
R2
is
square.
just write the VA and VB, right? What is VA?
Yes,
KQ1 by R1 plus
yes,
KQ2 by D square plus R2 square, right?
yes, sir.
But when we write VB, it will come KQ2 by R2 plus KQ1 by D square plus, and the work done formula is simply Q naught into VB minus V. That's it.
Yes, sir.
Yeah, just a minute. So what else we can do now? Hmm, hmm. All right, so we can do something like okay. So one is the self energy. And one is- Yeah. So now you can think for a while, but I think okay, I will solve this question eventually. So I think we have done this. I don't know. Calculation of potential at the okay, we missed this part actually, at the edge of uniformly charged disk.
No, sir, we can do this.
Yeah. So the question is, we have an uniformly charged disk. So we have calculated the potential at the center, right?
Yes, sir.
So what if we want to know the potential at the perimeter, periphery? So let's say I want to know the potential here, sigma square. So you think for a while how we can solve, then I'll solve.
Okay, sir.
So this is a actually trick based problem. So it's not something very simple which you can solve. Even for me also, until I haven't seen the solution, I was not able to solve. So the whole idea is it's a new trick. Okay, and the trick is mathematical trick. So am I audible to you?
Yes, sir.
So first we do a diameter. Just do a diameter. Okay, and then okay, I can choose the center, the point P here. That's easy for me. So to find the potential at point P, we need to have the charge particle which is having known distance from the P we can solve. So the way of doing is you take a circle, you take a circle whose center is P.
Okay, sir.
Because if this is
So
the
just a
center,
random circle.
yeah, no. Yeah, random circle only, of course. But the P should be the center actually.
Yes, sir.
Just I can do this better. Something like this. And the whole idea of taking such elementary is the distance of every point from this elementary to the point P will be fixed. So if I call this as R, it is R everywhere, isn't it?
Yes, sir.
Okay, fine. So what we do next is what we do next is we join the center of the actual circle, the disk to the edges. It may look weird. Maybe I should do even like this. Just move it slightly ahead. You can get the idea. Okay. So now, if this is the center, you can join. Just join like this, center to here, and this is R, correct?
Yes.
And the disk radius is capital R. So if I call this angle as theta, then this is also theta, and so this becomes 2 theta, right?
Yes, sir.
So essentially, we can write the small r in terms of capital R, isn't it? In terms of angle. So this is looks like 2r cos theta. And not only that, the charge on the elementary ring will be how much? Sigma into, so this is a dr, sigma into r2 theta. I hope you're getting this part, r2 theta part.
Yes, sir.
So sigma into r2 theta is the circumference, like the perimeter, into dr is the area, and sigma into area is the charge in this part. This part. Okay.
Yes.
So now we can have the potential at point P equals to KQ by R, which will become K sigma r 2 theta dr, okay, upon r. But we need to substitute r also, right? In terms of theta. R is 2r cos theta, so we can add dr equals to minus 2r sin theta, right?
Yes, sir.
Into d theta. Sorry. So now we can substitute everything.
So we could have cancelled that R and R in the numerator and denominator.
Sorry, I didn't see that. Yeah, this will cancel out. No? So in fact, we need not write even this these two terms. So this term is not required. Okay, yeah, fine. So what we are left with then? We are left with dvp equals to k sigma 2 theta minus 2r sin theta d theta, right?
Yes, sir.
So the answer is 4r 4r yeah, this one, no? And the question is, what is the integration of the limit of integration? So it will go from, so if you take theta equals to 0, you will be on the right edge. Theta is 90, will be on the left edge. So correct.
Yes.
Now this is difficult integration. Called this is called integration by parts, which I'll give you. So theta sine theta. So we use the UV rule. I let inverse logarithmic algebraic trigonometric exponential. So this is algebraic function, right?
Theta we consider it to be algebraic, sir.
Yeah, no, you can add like x sin x. Now it's algebraic, no?
Oh, yes, sir.
Algebraic, trigonometric, and that's it. So which one will come first? The algebraic will come first, then trigo. So we take UV. So the formula is what? U into V dx minus du by dx integration of V dx whole dx. That's the formula. Understood? This is the formula.
Yes, sir.
And using this formula, you can write as U V dx minus du by dx. I think U is x. V dx into dx. So this turns out to be sine. So the answer is this much. I mean, really big answer. Minus theta cos theta. Okay. And now if you put the limit from 0 to pi by 2, sine pi by 2 is how much?
1.
and cos pi 2 is 0, right?
Yes.
When you put the lower limit, it is 1. So the answer, this is 1 only. The entire thing is 1. So, so much of struggle and to get 1. So this term is 1 or minus 1 should come actually. So, okay, okay, the mistake is here. The R will go from 0 to 2R, right? So R will belong to from 0 to 2R, correct? The farthest point is this, and therefore the theta will change in other way. So theta will go from pi by 2 to 0. So I have to change the limit actually.
Upper limit and lower limit will be switched.
Yeah, minus 1 should come. That's why the answer is positive. Anyway, so whole idea is the potential is 4RK sigma. That's it. That's the answer. Because the other term is minus 1. And we can attach K as 4 pi epsilon naught. So the 4 cancels out, and what we get is very fine answer. Sigma r by pi epsilon naught. Earlier it was 2 epsilon naught, right?
Yes.
And now it is pi. Pi is more than 2, so the answer is the potential at the edge will be less than the center. Okay.
Yes.
So just remember the formula, and clearly we can see the edge will be at high potential than the center. Center was how much? So it is roughly 1 point like 0.3, and here this is 0.5. Okay. So now assuming you know the, so ignore this refer. So now we have to learn the two more concept, and that is called self energy. Okay. So what is self energy? It is also kind of potential, but it is not between two particles, rather it is between the particle belonging to the same system, in which we cannot distinguish. Let's say if I have a charge here and a charge here with some separation, you can see that we have two distinct charge.
Yes.
Okay. Just so if we have a discrete particle, we can distinguish and we can call, okay, we can say that okay, these are two particles, so they will have potential energy. But when you put a charge on a rod or a disc or sheet, Can we really distinguish this from this?
So, I mean, like the space, depending on the density, it might be very less.
In fact, the whole idea of continuity belongs to the lack of the space concept. So we because we don't see any tangible space, we call it continuous, right?
Sir?
So no, in the continuous charge distribution is what? You don't see any gap, no?
Yes, sir.
So let's say you
So
take a
in
uh,
actual reality also there is no gap, or like we
no,
are
no,
assuming it like that.
no. In reality, we always have a gap. Okay, but the
Yes, sir.
gap is small enough not to be visible. So it is
Uh,
like let's say you take a sheet of paper and you draw, or you draw infinite dots. So it is as good as the paper is filled with dots everywhere. So there is no gap. So the dots are like continuous. Understood?
yes. So if there is, I mean, like there is an observable charge
Yeah.
uh, in the macroscopic level. So I mean, there might be like so many countless number of electrons contributing to the charge. So
Yes.
there's
Yes. So it is like even a single dot which you can see will have just infinite number of electrons.
yes, sir.
So a dot which you draw will have infinite electrons. So if you zoom out, you will see just infinite electrons. Anyway.
Yes, sir.
So when you look in the night sky and if you look at a star, a single star which you see as a twinkling is actually composed of 2000 actual stars.
What?
A single star which you see in night sky is actually a cluster of 2000 stars.
So they're kind of like fused together, or
No, no, no. Because we don't see object, we see light. No?
yes, sir.
So the light coming from these distant stars are so close in terms of angle that we don't see they are distinct. They are like same. So you see the light, you see a single light spot. And the reality is these 2000 stars are itself light years away from each other. But you are, let's say, billions of light years away. So your perception of one star is not reality. Understood?
Yes, sir.
Similarly, the perception of continuity is not the reality. I mean, it's just a perception. So we should be happy with this nice perception because it serves all the purpose which we want.
Yes, sir.
So self energy comes into picture when we have a continuous charge distribution. So we say that every charge, possibly every charge distribution, or every you can say continuous charge distribution, will have mutual potential energy, which we prefer to call self energy, because we cannot say that this belongs to this or this charge. So there is no distinction of charge. So we call it self energy, the energy of the system, or you can say the energy that we need to impart in order to create such continuous system of charge. Okay.
Okay.
Now, technically, every charge, if I put a charge on a wire or disk or ring or whatever, every system of charge which is having continuous distribution will have self energy for sure. But it is not easy to calculate it mathematically in all cases. So we will only restrict ourselves to those cases or scenario in which the mathematical viability is there. So only when it is mathematically feasible, we'll go ahead, else we'll ignore. Okay.
Yes, sir.
So the two cases which are famous, and the third case which I can take extra, which is not part of JE. So the two famous cases in which we have to study actually about the self energy are the hollow shell and the solid sphere. So let's say the radius is r. In the first case, the charge is spread throughout the volume, which we call solid sphere. And the other case is when the charge is only kept over the surface. Okay. So if we have a charge over the surface, and if we have a charge which is spread throughout the volume, so again, when I'm saying the self energy, it is again the energy which we need to create such distribution. Okay. So we'll go one by one. And the way we define the potential will remain intact. So you can take some metallic conductor like a hollow shell, and you're trying to bring some charge from infinity. So what we do is we bring the charge dq and put it here, and after a long time, sorry, after a very long time, some charge will be there already, isn't it?
Yes, sir.
So let's say this charge which we have already kept here is q, and now we are trying to bring this charge from infinity. So we know the potential at infinity is going to be 0, and the place where you are trying to bring the charge will have some potential, the surface.
Yes, sir.
And we know the formula of surface potential of a uniformly charged sphere, right?
Yes, sir.
What is the formula?
KQ by R.
So now because you know the formula, yeah, that's correct.
Yes.
KQ by R. So what is the work done in bringing the dq charge? Only dq. Because we are bringing small charge, the work is also small.
Yes, sir.
And this will be how much? dq into
KQ by
potential
R.
difference. Yeah, very. And I hope it is integrable, right?
Yes, sir.
So if you integrate from 0 to capital Q, what is the answer now?
KQ square by 2R.
So this is the work done required to create this distribution, right?
Yes, sir.
Just Are you there? Okay.
So are you
Hello?
speaking something? I will.
No, 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 no. I just came actually.
Okay.
So, so now this answer is pretty simple. So the work done in doing this charging process will be equal to this value, and we are doing from taking the charge from 0 to the net value q, and the answer comes out to be kq square by 2r, right?
Yes.
So which is like so this work, where this energy will go, so we are not dissipating, right? So this will become the self energy of system. So you may be wondering where this energy is actually present. The answer is wherever you see the field, wherever you see the electric field in space, what you can understand is the energy, which means the field in electrostatics itself is energy. Yeah, field is energy. Understood? Field is energy. Okay,
Okay, sir.
and the field will be from where to where? Surface to the infinity, right?
Yes, sir.
And because there is no field inside, so we say the energy is spread from surface of the sphere up to infinity. So the energy is not actually at one particular place, it is spread throughout the infinite volume. Understood?
Yes, sir.
So but as you go away, the intensity will decrease, so maximum energy will get at few maybe centimeters ahead, then the answer will be very small. All right, so we'll also learn the alternative method to get the same answer. This is one of the answer, one of the way of doing this. Okay, so next is, you have some time.
So yes, sir.
So the next is solid sphere, right?
Yes, sir.
So solid sphere we don't create just like that. So in creating the solid sphere, we assume that the density we are trying to keep it constant. So we put some layer of charge, and initially it will be very complex to create the charge, but eventually my charge will look like this. So what I'm doing is from infinity, we are bringing dq charge, putting on a sphere continuously, and we're not just putting it, we are putting, or you can say we are smearing over the surface, like to create the uniform thickness. Understood?
So like hollow shell.
Yeah. So like hollow shell. So we create extra layer of hollow shell. You can think that.
Okay, sir.
So a very thin layer is just formed because of the dq charge which we have just brought. So the dq charge will be kept over the surface like this, and as a result of every charge which we add, let's say the charge which you have already brought is small q over this volume, and extra charge which you will keep will increase the thickness by dr. So the formula is same, but can you try to derive this answer? Like you can try for once at least.
Okay, sir. Sir, are you able to hear me?
Yes, yes. Tell me. That's what.
Sir, I'm getting the answer is 3/4, sorry, 3/5 kq by r. Sir. Yes, sir. 3/5 kq square by r.
Excellent. Very good.
Thank
And
you, sir.
as always, proud of you. Okay, so I think with this question we complete the potential energy part up to energy part, and now we are good to go with the uh, two more concepts. One is called the electrostatic pressure, and other is called the dipole moment. So I think one more lecture will be sufficient to finish this. Hopefully,
Okay, sir.
just let me check. Yeah, dipole will take some time. That's true. Okay, yeah. So we can stop here for the day, and next lecture will finish the remaining portion of electrostatics. It will take. So in future we will be done with
So your Harrison?
Hello, hello, hello.
So now I'm able to hear you.
Hello, hello.
Yes, sir.
Am I audible?
Yes, sir. Now you're audible, sir.
Okay, fine. So no, it will take two more lectures for dipoles. Okay, that's a
Okay,
big
sir.
topic. And then after that we can go for. So what I'll do is I'll finish the gravitation chapter from 11 because electrostatics and gravitations are almost same. So it will be easy
Okay,
if
sir.
I finish the gravitation as of now, so that we also finish one chapter from 11th portion, and then
Yes,
we
sir.
can start the next chapter called capacitors. All right. Okay.
So gravitation chapter, how many lectures it will take, sir?
I will not take more than two lectures
Okay, sir.
because it's,
So can
everything is same. Just yeah, tell me.
yes, sir. So can we have extra class tomorrow?
Tomorrow is Friday, na?
Yes, sir.
Yeah, tomorrow. Yeah, I can take one. No, no.
Okay, sir. So in the morning or afternoon time?
Hopefully in morning around 10 o'clock.
Okay, sir.
But I will let you know. I will let you know because I have to schedule. I haven't scheduled for tomorrow. So once I will schedule, then I'll.
Yes,
But
sir.
we can keep, yeah, we can keep tomorrow one lecture. Again, from next week till the month of May, we'll keep just two lectures. But again, from the June, I'll increase the lecture because your summer vacation will start, right?
Yes, sir.
So when it is starting, summer vacation?
So summer vacation is starting from June 10th, I think so.
Okay, fine. So from June 10th, I will keep extensive number of lectures. So, but in any case, the number of lectures we cannot exceed more than three, but we'll increase the hours. So now I'll keep the 3 hour lecture minimum. Okay.
Okay,
So
sir.
in that way, in 1 week we will have like 9 hours, which is as good as 4 lectures, isn't it?
Yes, sir.
Yeah. And at one stage we can pull more content out.
Okay, sir.
Good night. Take care.
Good night, sir. Thank you, sir. Bye, sir.